Hello everyone, welcome to aplusbi. This channel is all about complex numbers, and in this video we're going to be solving a locus problem with the arg function, which is the argument. So let's go ahead and quickly talk about the argument of a complex number, and then we'll get into the solution. Okay? Alright, great. So the argument of a complex number z can be defined as theta if we can kind of plot z on the argand plane as follows. So we have this z right here, and as you know, z has a real part and an imaginary part. Let's just call them x and y for now. Sorry, aplusbi. I know it's the name of the channel, but I just need to use x and y here because we're going to get into the locus problem. Okay, so this is the real part, the imaginary part, no offense, and then this is going to be the theta. Of course, theta is measured in the positive direction, which is counterclockwise, so on and so forth. And obviously, theta is not the only angle. This is just the principal value or the principal argument. Make sense? Because you can add multiples of 2 pi and you'll get to the same point. And that's the point. Okay, great. So that's basically the argument, but we have a more complicated, I don't want to say complex, it is complex, but it is complicated expression because we have the ratio or the quotient of two complex numbers. Z is a complex number. We have to evaluate z minus 1 over z plus I. So let's go ahead and do it by setting z equal to x plus yi. I want to focus on this first, and then once I simplify it, I'm going to plug it in because I don't want to write the arg every time. I'm lazy. That's who I am, okay? Now, replace z with x plus yi minus 1, x plus yi plus 1. Now, you can kind of rearrange these terms, put the real parts together and imaginary parts together, or just imaginary part. And then we can kind of do our little hocus pocus, which is the multiplying by conjugates, right? It's not really hocus pocusy, but you get the idea. This is the real part, so I'm going to multiply this by x plus y minus yi, which is going to give us the conjugate. Notice that I'm kind of emphasizing the fact that it's, you know, is in parentheses. It doesn't have to be, and then it's going to look like this. Well, putting this in parentheses actually kind of helps because now we want to multiply the real parts by real parts to get a real part, or part of the real part. It's not the whole thing, okay? Anyways, hopefully you get the idea. Hopefully I did not confuse you. Now, we're going to go and multiply this and simplify as much as possible. X minus 1 and x plus 1 is going to give me x squared minus 1 from difference of 2 squares. And then these two guys is going to give me minus y times x minus yi. I want to put the I at the end. And then these two guys is going to give me y x plus 1 I. And then at the end, yi and yi is y squared, I squared, but there's a minus sign. I squared is negative 1. So this is going to be plus y squared. Get the idea? And divide the whole thing by. Now, what happens if you multiply a complex number by its conjugate? You get sum of two squares, not difference. Be careful. It is always a real number, by the way. Okay? And it's always non-negative. You don't want it to be 0, obviously, in this case, right? Cool. So that's my thing, the quotient. Now I need to arg it, right? I mean, find the argument. And the argument is supposed to equal pi over 2. What's that supposed to mean? Who knows, right? Let's go ahead and simplify this a little bit before. So if you kind of focus on the imaginary parts here, you'll probably notice something like this. Minus xy plus y, and then there's an I, obviously, at the end, which I'm going to put that, plus xy plus y, and the whole thing multiplied by I. Notice that xy cancels out, leaving us with 2yi. So that's my imaginary part, cool, and the real part is fairly easy. So here's my expression, x squared plus y squared minus 1. That's the real part. And then plus the 2yi is the imaginary part, I mean the 2y only. And then that divided by this. Now, at this point, you're probably thinking tangent, right? But I'm going to go off on a tangent and use something else. Here's what it is. I'm going to separate the real and imaginary parts like this. Okay, like this. And like that. The denominators are going to be the same, of course. And this whole thing is multiplied by I. Great. So now I can clearly see the real and imaginary parts. And that was important because I'm about to set this equal to what? I'm about to set this equal to cosine of theta, and this one to sine of theta. But here I'm making an assumption. Is that always going to work? That's a good question, right? Well, the assumption that I'm making is that the modulus for this number is 1. Okay, that could be dangerous. We're going to check that at the end when we find the number. But you could probably proceed a little differently. And anyways, let's just get this done. Let's get it over with. So by assuming that this is cosine, this is sine, and I know that theta is pi over 2 because that's the argument, I know cosine theta is equal to 0, so that would be fairly easy to handle, right? Because it's just 0. So if you set this equal to 0, what are you going to get? The numerator is 0, right? From here we get x squared plus y squared equals 1. Great. By setting the sine, the imaginary part, to 1, which is sine theta, right? Or sine pi over 2. You can see here it's 1. I'm getting something else. Let's expand the denominator. X squared plus y squared plus 2x plus 1 equals 2y, because we're cross multiplying. And we know from the first equation that x squared plus y squared is equal to 1. So this is 1. 1 plus 1 is 2. So we get 2x plus 2 is equal to 2y, which means y is equal to x plus 1. Great. Now here's something that we can use. How? We can go ahead and actually, I think, did we make a mistake? No, I don't think so, because we got 2y. I was thinking about this like it's a 2yi, right? Not a yi. Okay, good. I think this looks good. And now we're going to have to solve this system, right? But that's fairly easy. Let's replace y with x plus 1. X squared plus x plus 1 squared equals 1. X squared plus x squared plus 2x plus 1 equals 1. 1 cancels out, and we end up with 2x squared plus 2x equals 0, or 2x times x plus 1 equals 0. Beautiful. Now from here we get two simple equations, such as x equals 0 or x equals negative 1. Now if x is equal to negative 1, what happens to y? That's what we got to find out. For that, we're going to use either this equation, that equation. Doesn't matter. First one is easier, the top one. Y equals x plus 1. Y is always 1 more than x. So if x is 0, y is 1. If x is negative 1, y is 0. What's that supposed to mean? It means that our complex number can either be written as z equals I from here, and from here z equals negative 1 plus 0i, which is negative 1. Here's the million-dollar question. Do these solutions satisfy the original equation? That's a good question, right? Let's go ahead and check it out. Now, when we plug these in, first of all, if z is negative 1, we're going to have an undefined situation, which is not good, too bad. What about z equals I? Let's find out. So it's going to be argument of I minus 1 over I plus 1. Let's multiply by the conjugate. This should be 1 minus I and 1 minus I. So we're kind of like squaring 1 minus I, which is negative 2I, and negating it, which is going to give us 2I, which is kind of interesting, right? Okay, this is going to be 2I, and this is going to be a 2 from sum of two squares, and the argument of I is actually pi over 2. So that seems to work, even though I assumed that my number has a modulus 1, but can we do it a little differently? And also, can't we just use tangent pi over 2? That's a good question, and that's for you to answer. And this brings us to the end of this video. Thank you for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care, and bye-bye.